Hello, welcome to lecture number 8. Again, this is our lecture number 8, and our topic today is higher order derivatives. This is the last section of chapter 9 of the course textbook, higher order derivatives. So our main objective is how to find second derivatives and also higher order derivatives of certain functions. What we mean by higher order derivatives is that previously we always find the first derivative of any function, find the derivative of a function. Now we can say, okay, find the second derivative of a function or find the fourth derivative of a function. When they say we should find the second derivative of a function, it means we are going to use the same derivative rules, both sum, difference, quotient, power, product, all the rules, what we went through. But this time I'm going to find the derivative of a function, then I'm going to find the second derivative of the function, then the answer for the second derivative of the function, I'll find the derivative of it again, which will be the third derivative. The answer for the third derivative, I'll find another derivative of it again, that will be the fourth. So that's what we mean by higher order derivatives. We are going to look at an example right now. So here we can see the symbol we are using here. The first derivative, we have only one apostrophe. Second derivative, we are going to have two. Third, three, fourth derivative, etc. So the whole concept of, again, higher derivatives means we're going to find the first, the answer of the first derivative, you can find the second. The answer of the second derivative, you can find the third. So first, we're going to do an example on how to find the second derivatives. So this is an example given to us. They say we should find the second derivative of y equal to s to the power 4 minus 3s squared plus s to the power negative 2. B also, we're going to find f at x equal to s and 3s cubed minus 4s squared plus 5. We need to find the second derivative. So let's see the first one. As we said earlier, here we are looking for the second derivative. So we need to find what? The first derivative. So we know the rules already. This is a power rule. So this will give me 4s cubed. Minus 3s squared will give me 6x. X to the power negative 2 will give me minus 2 to the power negative 3. So we get 4s cubed minus 6x minus 2s to the power negative 3. The reason why it's negative 3 because negative 2 minus 1 will give me negative 3. And also negative 2 have to be in the front. So it will change the sign positive to negative. So this is our first derivative. We know how to find this. Now, the question says find the second derivative. So we need to find the derivative of the first derivative. So 4s cubed will give me 12s squared. 6x will give me 6. Then we have minus 3 times minus 2. So that will give me plus 6. And minus 3 minus 1 will give me minus 4. So here I'll get minus 3 times minus 2 plus 6, minus 3 minus 1 minus 4. So we get plus x negative 4 plus 6x negative 4. So this will be the second derivative, 12s squared minus 6 plus 6x to the power negative 4. So now if, for example, they say we should find the third derivative, then it will be 2 times 12 is 24x, and this will give us 0, minus negative 4 times 6 will give me minus 24. So it will be 24x minus 24x to the power 5. So let's try the second example. We know the question was, let's go back to the question again. The question was 3s cubed minus 4s squared plus 5. So I'll find the first derivative. The first derivative will give me 3 times 3, which will be 9x squared minus 8x. So we get 9x squared minus 8x. After that, I'm going to find the second derivative. So the second derivative will give me 9 times 2, which will be 18x minus 8. So 18x minus 8. And that will be our solution, second derivative. Now, if we need to find a third derivative, then it will be 18 minus 0, so 18. So sometimes it's very common to use the second derivative. We say d square y by ds square, or d square f at x by ds square. And this would denote the second derivative because it's second square. If it's third derivative, we say d cube y by ds cube. So now let's go through the higher order. When we said higher order derivative, we mean it can be more than second, third, fourth, fifth, sixth, any amount. Those are higher order derivatives. And the concept is the same as we just saw for the second derivative. Now, if it's a third derivative, we say d cube y by ds cube. Fourth derivative, we say d to the power 4y by ds to the power 4. That's the symbols we use. But again, we are still using the same derivative formulas or rules. This time we just have to find what the higher order, second, third, fourth in the amount. So for example, the question here says, find the first 4 derivatives of f at x equal to 4s cubed plus 5s squared plus 3. So here we are looking for the first 4 derivatives. So I need to look for the first, second, third, and then fourth. So the first derivative, I'll get 12s squared plus 10x. So let's see, 12x squared plus 10x. Then the second derivative, I will get 24x plus 10. 24x plus 10. Then the third derivative, I will get 24 plus 0, so just 24. We are looking for 4, so 4 will be a constant value, 0. Now, if I'm looking for fifth, it will be 0, 6, 0 throughout. So this will be, again, the fourth derivative of f at x equal to 4s cubed plus 5s squared plus 3. The answer will be 0. So you can see how we follow step by step. We find the first derivative, second, third, then the fourth. So we have an application question here. Here they say, by using International Telecommunication Union and key global telecom indicators data from 1990 and we projected to 2020, the billions of world cell phone subscriberships can be modeled by the following function. So by predicting from 1990 to 2020, we have a model that we can use, which is 0.895 t to the power 3 plus 30.6 t to the power 2 plus 2.99 t plus 55c. T will be the number of years that passed 1990, because it's from 1990 to 2020. Now the question says, find the instantaneous rate of change of the worldwide cellular subscribers. So here we're just going to look for the function, which means we have to find the derivative. Then find the instantaneous rate of change of the function found in part 1. Then for what t value does the second derivative of c at t equal to 0? So we have to find. Then find the instantaneous rate of change of the world cell phone subscriberships from 2005 and in 2015. Then we use the second derivative to approximate how fast the instantaneous rate of change of the world cell phone subscriberships is changing in 2005 and in 2015. We should explain the meaning of C derivative 25 and then the second C derivative 25. So let's start with the first option. We have our function, so we find the first derivative. We can go back. So first derivative will be negative 0.895 times 3 t to the power 2 plus 2 times 30.6 t, then 2.99t. And I can see that, so sorry, 2.96.296. Let's make sure there's 2.99t. Yeah. So we find the first derivative, the same concept, then the second derivative. Then our condition, we equate it to 0. We say we want to know when t is our time, so we are looking for when second derivative. Again, let's look at the question. From what t value does the second derivative of c at t equals 0? First, we find the instantaneous rate of change of the cellular subscribers function. That is finding the first derivative, c at t. Then find the instantaneous rate of change of the function found in part 1. Or part A. Now for what t value, so here we can see that when we get our second derivative, then we equal it to 0, because here the question said, for what t value does the second derivative of c at t equals 0? Equals 0. So find the second derivative of c at t, then equal the answer to 0. Then you find the t value, and that's what we did here. If we get a second derivative, then we equal it to 0. Then we look for the t. So that's the first. A is the instantaneous rate of change of c at t is the instantaneous rate of change of c derivative at t is the second. Then to find the t value, we equate it to 0. Then we solve for the value of t. T is roughly 18.96. So the second derivative c at t equal to 0 in 2009. Roughly we say 2009, which we are assuming here is 19. D said we find this rate of change by evaluating the derivative. So we find the first derivative at 15, then at 25. Because looking at the question, they say, find the instantaneous rate of change of the world cell phone subscribership from 2005 to 2015. So that's roughly, I would say, 10 years. So we solve for the following, and we got 18.96. D, we find this rate of change by evaluating the derivative. So we know in 2005, we find the derivative of c at 15, which we substitute. Then derivative, the first derivative at 25, and the second derivative at 15, and second derivative at 25. You can see the first derivative was 0.409, but second with the same 25 become negative 0.0264. And we can see that the first derivative at 15 was 0.455. Second derivative at 15 was 0.0173. So in 2015, the number of world cell phone subscribers increased at the rate of 0.409 billion per year, but the rate of change decreased at the rate of 0.0264 billion per year. So this will be the conclusion of our lecture number 8, which cover again higher derivatives. And as usual, we're going to solve more examples, questions, and post it also. So please, you can comment or like it or subscribe to this channel. Again, the channel name is Charles Ebeke. Thank you.